remembrance-kjv.com, video number 13. You are welcome. This video was intended to be on Egyptian multiplication by doubling. However, it has been committed to simple multiplication associated with Yoruba's vigesimal number system. There is nothing wrong in representing the vigesimal base using 20 different numerals, but additive and subtractive notation are convenient for mathematical thinking and mathematical calculations. The table shows additive version of the vigesimal notation and the double for each numeral. After a half of the base, the numerals repeat, and the only difference being a dot above the numerals. If the additive sign, the dot, is removed, the unit values of the doubles also repeat 4 times till we get to circle. The doubling trend becomes easy to study. One needs to know the doubles from 1 to 5. The doubles from 6 to 9 are similar to those of 1 to 4, except that they bear a dot above them. The unit values of the doubles of 13 to 19 are the same as the doubles of 1 to 9 respectively. On doubling a digit in a number, if a digit to its right is dec or a team, that is, if it bears a dot above it, then the unit value of the double is increased by 1. It is the double of the most significant digit that is written as it is, or with an added carry digit. As for the rest of the digits, only the unit values of the doubles are written as they are, or with added carry digits. Let us try and double the number 8 of 13, 90, 15, 76. The double of a dot number leads to a carry 1. The double of 18 is a carry 1, so we first write down 1. The double of 8 is 16, but 16 is increased to 17 because there is a dot 1 to the right of 18, so we write down 17. Double 1 is 2, and we write down 2. Double 9 is 18, plus a carry 1 from the dot 5 to the right, so we write down 19. Double 5 is dec, and we write down dec. Double 7 is 14, and we write down 14. And double 6 is 17, and we write down 17. Therefore, the double of 8 of 13, 90, 15, 76 is a score 17, 2019 dec, photo 17. Let us double again this result, but this time faster. 2, check, 3, 14, check, 14, 4, check, 5, 18, check, 19, 0, check, 1, 8, check, 9, 4. The solution is 30, 14, 50, 19, 194. That is easy and swift. It should be noted that to carry out this doubling activity, one needs only to know how to double numbers from 1 to dec. The rest is achieved by careful study of doubling patterns. You also present the hexadecimal, base and the bidecenal base in a similar numeric representation and practice repeated doubling. Let us revisit a numeric representation of the Yoruba number system. Since we are taught to deal with base 10 calculations, it is easy for us to carry out multiplication for numbers 10 and below, even if the result is supposed to be presented in vigesimal notation. For calculations involving high complex numbers, it is a little bit demanding unless one is taught how to go about it. We should remember what we learned from video number 11. When multiplying using half of the base, one has to suffix a 0 to the multiplicand and then divide the result by 2. Let us take an example of the multiplication between one high complex number and a number below half the base. Let us take 8 multiplied by 17. This is the same as 8 multiplied by the bracket of 10 or dec plus 2. 8 by 10 is 4 score, and 8 by 2 is 16. 4 score plus 16 is 4 score 16. Therefore, 8 multiplied by 17 is 4 score 16, or 4016 vigesimal. A second example is 6 multiplied by 17. This is the same as 6 multiplied by the bracket of 10 plus 7. 6 times 10 is 3 score, and 6 times 7 is 2 score and 2. 3 score plus 2 score 2 is 5 score 2. The final product is therefore 5 score and 2, or simply 52 vigesimal. When multiplying high complex numbers, one has to take advantage of only 3 algebraic algorithms. The first is the bracket of x plus a multiplied by the bracket of x plus b is equal to x multiplied by the bracket of x plus a plus b plus the product of a and b, where x is half the base, and in this case 10. An example under this algorithm is the multiplication of 13 and 15. The calculation gives 10 multiplied by the bracket of 10 plus 3 plus 5, then plus 3 times 5. 10 plus 3 plus 5 is 18, and 5 times 3 is 15. 10 is a half score, and 10 by 18 is 9 score. The solution, therefore, is 9 score 15, or 9015 vigesimal. The second algorithm is expressed as the bracket of x minus a multiplied by the bracket of x minus b is equivalent to x multiplied by the bracket of x minus a minus b plus the product of a and b, where x is the base. As an example, let us carry out the multiplication of 16 by 17. 16 is a score less 4, and 17 is a score less 3. Score less 4 multiplied by a score less 3 gives a score multiplied by the bracket of a score less 4 less 3, and then we add the product of 4 times 3. A score less 4 less 3 is 13, and 3 times 4 is 17. The final calculation gives 13^17 or simply 30^17 vigesimal. The third algorithm results from the modification of the second algorithm. If instead of A and B in the second algorithm we use .A and .B respectively, the algorithm reads as follows. The bracket of x minus .A multiplied by the bracket of x minus .B is equivalent to x multiplied by the bracket of x minus .A minus .B, then plus the product of .A and .B. Making the product of .A and .B subject of the formula gives the product of minus x and the bracket of x minus .A minus .B plus the product of the bracket of x minus .A and the bracket of x minus .B. Multiplying the bracket by the minus sign gives x multiplied by the bracket of .A plus .B minus x plus the product of the bracket of x minus .A and the bracket of x minus .B. But .A is half base x plus A and .B is half base x plus B. Grouping like terms inside the bracket gives x multiplied by the bracket of A plus B plus half x plus half x minus x plus the product of the bracket of x minus .A and the bracket of x minus .B. The final algebraic formula is the product of .A and .B is equivalent to the product of x and the bracket of A plus B plus the product of the bracket of x minus .A and the bracket of x minus .B. This algebraic expression is also interpreted as the product of a number which is A more than half the base and a number which is B more than half the base gives a solution whose base value is A plus B and a unit value which is the product of the bracket of the base minus .A and the bracket of the base minus .B. As an example, 16 multiplied by 17 gives the number of scores that are equivalent to 6 plus 7 and a unit value equal to the product of a score less 16 and a score less 17. Score less 16 is 4 and score less 17 is 3. 6 plus 7 is 13 and 4 times 3 is 17. The product of 16 and 17 is therefore 13 score and 17 or simply 30^17 vigesimal. Using the same algorithm but in base 24, we have decteen multiplied by 19. This gives the base value which is equivalent to dec plus 9, which is 17 bidecenal, and a unit value of 2 times 3, which is 6. The solution is 7/6 bidecenal. If you can remember, this is the algorithm that was presented on the Belgian theater show, Africa Plus. So, Yoruba number system is presented in a format that favors algebraic approach to number times. From the trends that can be deduced from the number system, it also is easy to introduce ways of how to manage multi-base calculations. These are some of the riches of the Yoruba number system. More riches will be disclosed in future videos. Thank you. Do not forget to subscribe to this channel. Meet you in video number 14, where we will take a look at Egyptian multiplication by doubling.